Okay, so thank you everyone for attending here and remotely. I'm Richard Newell. I'm chairman of the Cryptographic Extensions Task Group, and this is Ken Dockser, who's our vice chair. Let me introduce very briefly. I work at Microchip and do FPGA security about a dozen years. They're doing that, and I started with the RISC-V security committee the first day there was a RISC-V security committee, and there were two of us, me and Joe Zai. And today we have a dozen very active members in this group, but we have 314 members just in this cryptographic extension task group. And now instead of one security committee, we have like a dozen security committees. So things are really moving, and we're at a critical juncture here with the Vector crypto instructions. For Ken, just say a word or two about Ken also. Ken is a CPU architect with, I looked through his resume, I can't possibly go through his whole resume right here, but I see it has everything from DEC-VAX and ARM and x86 and RISC-V, and he's been doing RISC-V for a number of years at the previous company, and now he's here at Rivos. And I'd like to really make a shout out to Ken and Rivos, who have done really all the really heavy lifting on the Vector extension. And I'd like to remind people about our Scalar extension, which was ratified at the end of last year, and a big shout out to Ben Marshall and Marku's sitting right up here in the second row. And they created the Scalar instructions and the entropy source and the data independent timing specs that we got ratified last year. And as Ken is about to tell you, we're getting very close to freezing and then hopefully ratifying the vector spec. So there you go. One more thing on this slide. That's the present. Then the future. We have some plans to do one more set of AES instructions. We call them the full rounds AES instructions, and the idea is that will enable people to build implementations which are protected against side channel analysis, which is essentially impossible with the current set of extensions. We'll be looking more at post-quantum, although I would say that even today we have pretty good support for post-quantum because one of the most computationally intensive parts of post-quantum is the hashing, and they use the SHA3, and we already have quite a bit of support for accelerating SHA3. So even today, there's a lot of support, and we'll look at more focused support for post-quantum in the future. And then there could, then kind of who knows, there could be other cipher suites. We have AES and some Shangmi instructions in the current extensions. We've started to look at GHASH extensions and other kind of national ciphers or ciphers which are used specifically in 5G or other market verticals. Okay, finally, there you go, Ken.
Okay,
take it away.
You. Okay, so in the next 18 minutes or so, I'm going to answer the age-old question.
Are you getting amplified?
Can you hear?
Can you
hear me? Is the microphone on? Okay. Age-old question of what is cryptography. I'll give you a RISC-V vector extension refresher, basically go over some basics, because of course vector crypto is built on top of the vector extension specification. I'm going to talk about vector element groups, which is necessary for the wider data that we're operating on in crypto vector, some new vector scalar instructions, a really new type of instruction, and then I'll go over the 6 vector crypto extensions that we've defined. So cryptography is a means of protecting information through really 3 prongs. There's confidentiality, there's integrity, and there's authenticity. So the confidentiality is handled by encryption. It makes sure that even if somebody intercepts your message, it's garbage. They can't understand it. You need a key to be able to read the information, to access the information. Integrity is a way of proving that the information hasn't been changed. It could be that you send a encrypted message, a third party intercepts it, they do some bit manipulations on it, and before the receiver gets it, they decrypt it, and they get something that has false information. It's a forgery. Depending on how much information the attacker has, they can actually change important things. They're not just, scramble it up. So you want to have a way of knowing that nobody has messed with the encrypted message. And so we use secure hashing for that. And then the third prong is authenticity. That's a digital signature. That's not something that we have addressed specifically in these extensions. That's more of a public key issue. So we do provide encryption with AES and the Chinese standard SM4. And then for secure hashing, we support SHA2. We have specific instructions for that. We have instructions that help accelerate SHA3. We implement instructions for SM3 and for GHASH. So quick refresher on the vector extensions. So the vector extensions have 32 registers, and then there are two parameters that all vector implementations have. One is VLang. It's the length of the vector, or some may think of it as the width. How many bits are in each vector register? For the V extension is the vector extension for application processors. VLAN is defined to be at least 128 bits. Okay, and then the other parameter is ELEN. And ELEN is despite its name, it's the width. It's the maximum element width in your implementation. And for the V extension, that's 64. So element sizes start at 8, and then they go up by multiples of 2, so 8, 16, 32, and then 64. So those are the 4 different element sizes that you can have in the V extension. There's also a concept called register groups, where you can combine registers together to be used as a single operand. So, for example, you can combine register 0 and 1 to be, basically you're concatenating the two to act as one operand for an instruction. So it's kind of one long vector rather than just 128 bits. If your VLAN is 128, you can be operating on 256 bits. And then instructions, there are lots of vector instructions. There are load and store instructions. There are instructions to set the configuration. The configuration is things like VL, which is the vector length, the V type, which gives you information about the width of the data, the operand size 8, 16, 32, or 64. And then the instructions, I didn't want to say SIMD here, they operate on multiple elements. You can do floating point instructions, permute instructions, integer instructions, but they're all operating on these 8, 16, 32, or 64-bit elements within the vector registers. So vector crypto can be built on top of any vector extension base. So the vector extension specification talks about an application processor base, which is the V extension, and then there are also some smaller embedded extensions. Implementing V or vector crypto on top of V with a vector length of 256 bits or more is ideal, because some of our instructions operate on data that's 256 bits wide. V length of 128 bits is fine as well. But then when you start using a vector implementation that's more narrow than that, there's some instructions that just won't work. So here I say an ELEN of 64. So that's the Scalar processor. If it's just built on RISC-V 32, there's some instructions that won't work. And then also if XLEN, I'm sorry, I think I said that backwards. If XLEN is the scalar width, if it's less than 64, meaning if it's 32, then there's some instructions that won't work. ELEN is, as I was saying, for vector, it's the maximum. It's the maximum element width. If ELEN is less than 64, there's some instructions that won't work. Okay. So, and these are all in the specification. Specification is near ready to freeze, so we encourage you all to go look at that and let us know if you have any comments or questions. Okay, so here I'm going to talk a little bit about element groups. So element groups are a way for us to deal with data that's wider than 64 bits, which is really the limitation in the base vector extension right now. So this isn't something that's unique to vector crypto, but we are the first ones to actually use element groups. In the future, other groups may be using that for things like matrix multiplication, complex arithmetic. There are two main properties of an element group. One is the element group size, which is the number of elements in an element group, and then the other is effective element width. That's the width of each element within an element group. And then there is the element group width, which is really just the product of the two previous numbers, the number of elements in a element group, and then the width of each of those elements. But when you specify the length of the vector you're working on, VL, it is in the number of elements, not the number of element groups. So I've got an example here on the top. So this is for an implementation that has the ideal vector length of 256 bits, or wider is good, okay? And then this is, for example, an AES instruction. So our element group width is 128 bits. Okay, the keys are 128 bits, the data that we're operating on. The effective element width is 32 bits, okay? And then we have the element group size of 4. So 4 times 32 gives you the 128 bits. The vector length here, so in a 256-bit register, we're operating on two values, 228-bit values. And on the bottom, I have element group 0 and then element group 1. And then the number of element groups to update is VL, vector length, divided by the element group size. So in this case, VL is 8, and the element group size is 4. So here we're going to be updating 228-bit results. We're going to, in this case, we'll do 228-bit encryption steps, for example. Another way you can use the element groups is if you have a narrower implementation. If your vector registers are only 64 bits, for example, you can set LMUL, that's the multiplier, part of the base vector extension. If you set LMUL equal to 2, then you're telling the machine that you want to combine two 64-bit registers together to effectively make a 128-bit register. Using the element groups, you can define an element group width of 128 bits, which is comprised of 32-bit elements, 4 32-bit elements. And in this case, we're just doing a single 128-bit operation. And so you can see that register VN is holding the lower part of the element group, and VN plus 1 is holding the higher part. So it could be, for example, register 0 is holding the low part, register 1 is holding the high part. Okay. So here's the actual element group sizes that are used in vector crypto. So for AES instructions, the element group width, really the data size, is 128 bits. The effective element width is 32, and the effective groups, or the element group size, is 4. And you may be wondering, well, why did we do 32, or in some cases 64? And that's because in many of these, when you're implementing many of these algorithms, you have to do some operations between the vector crypto instructions. And for AES, the common operations would be 32-bit. For, if you look down on the third row, SHA-512, the operations that you would be doing are 64 bits. So, and then I put in red kind of the outliers. So most of the instructions, the element group width is 128 bits, but for SHA-512 and then the SM3 hash, it's 256 bits. And then most of the element group sizes is 4 elements, but in the case of SM3 hash, it is actually 8 32-bit elements. And that's because the other calculations inside when you're implementing SM3 are 32 bits. So we have a new type of vector scalar instruction. This is different from what's in the vector specification, but it allows an element group to be used as a scalar. It reuses the VS suffix, something that already exists in the vector extension, and it allows you to apply a scalar element group to all lanes. So for example, if you're doing AES encryption, you can be using one 128-bit key for all lanes, all 128-bit lanes. So that saves you from having to splat that key and slow down the performance. So these are the 6 extensions that we have defined. Each is optional because at different parts of the world, people use different specifications. Some of these extensions require more hardware than others, so people might not want to implement some of them. The first one, Z, V, K, and S. So Z is the standard Z, V is vector, K means crypto, N stands for NIST, and S is, I forget what S was. No, I was going to give you a little cheat sheet there.
Sweet.
No, I don't think it's sweet. It's, it'll come to me in a second. So ZVKNS is the extension that supports AES. So we have AES key generation instructions. We have AES round instructions. Then for the ZVKNH, H stands for hash, we have an A and a B extension. And these are to support SHA-2. The A extension supports SHA-256. The B extension is SHA-256 and SHA-512. The ZVKB is bit manipulation instructions that are useful in cryptography. These are some of the instructions that accelerate SHA-3. They're also general purpose bit manip instructions. You can even just implement that even if you're not interested in cryptography because it has other useful things like bit reversal, endian swap, carryless multiply. The ZVKG is a vector GHASH acceleration. This is used for GCM mode, which you may do with AES or SM4. It is a single instruction that does a round of GHASH. So it's a very powerful instruction. It is very large. It requires 128 by 128-bit carryless multiply. One could implement it over several cycles reusing logic or just building the full multiplier to get the highest performance. And then the last two are for the Chinese cryptographic standards, the Shangmi instructions. So there's the SM4 block cipher, some ways similar to AES, but has enough differences as well. One of the differences is the encryption and decryption is the same. Whereas with AES, you actually have to swap the order of some of the operations. And then ZVKSH, the Shangmi suite, secure hash, includes 2 instructions to accelerate the SM3 hash. So, as I said, we're almost frozen. We thought we were going to be frozen before today. I was hoping to tell you we were frozen. Maybe later this week or next week we will. And then it will go out for public review. Here is a easy-to-remember link. You can just Google RISC-V-crypto. It works really well. Look at the spec. Ask us questions. If you find typos or something that's unclear or wrong, hopefully not too much there, let us know. Now is great or during the public review.
All right, we have time for one question. Irma's got her hand up here. She wins. Here you go, Irma.
Thank you. For the list of cryptographic extensions, are there any that are subset of the other ones? And also, are there dependencies or implications that we must bring some other extension in order to use those instructions?
So I'm sorry, I was having a little trouble hearing that. I think you were asking if there were dependencies for other instructions.
For other extensions,
other-
yes, as well as subsets. If one of the extensions were subsets of others that were listed in the previous slide.
Okay. So there are other vector instructions that need to be executed to implement some of these algorithms. In some cases, it's as simple as load and store instructions. Other cases, it could be add instructions, slide up, slide down. So yeah, you do need to have a full vector extension implemented, but it can be any vector extension. It doesn't need any floating point instructions or anything like that. And I think the other part was you were asking if some extensions kind of built, some of these built on others. No, so I can go back. So each of these is independent. They don't require the other to do it. Now, that said, if you want to do GCM, you're going to want to do the Galois counter mode. You're going to want to do that with some sort of block cipher. So you're going to want to implement, AES or SM4. Or you could use another block cipher that you build out of vector instructions as well.
Excellent. Thank you very much. So let's give Ken a round of applause, Ken and Richard. Yep. Thanks, guys. Appreciate it. Nice job.